We're going to take Desmos and we're going to plot a sine wave to see how it works so we can play with it as a simulation of sound. Use the letter T for time. Even though it's an angle, you're going to find you're going to want to use time T, not X. I'm going to move this over because I'm not interested in what's to the left of the axis because it's symmetrical. You may have known that the sine of an angle, right, goes between 0 and 1. So if I bring up a basic calculator, I can go 90 sine and I get 1. But that's the highest there is, and this high point here is not 90 degrees. It's some sort of weird number. And when I click on it, Desmos tells me it's pi divided by 2. What's going on here? Well, 180 degrees should be 0. Now it says pi. What's going on with that? Then I go down here and it says 3 pi over. What the heck is it doing? It's in a mode called radian mode. It's plotting by fractions of a circle. One entire circle is 2 pi r. This is eventually going to be your go-to place for angles. On a calculator, you will see this thing called radians. And if you go into radian mode, you can no longer use degrees. Instead of 180 degrees, you can use pi. It won't work anymore. 180 will return nonsensical results if you're in radian mode. But if you put in pi in radian mode, you will get the same answer that you would have got using 180 degrees in the mode you are most used to. What are we going to do with this now? Well, I would like to bring you up to speed on radian measure to make next year a little bit easier, but it's not essential. For right now, once you click on that tool, you're just simply going to hit degrees and convert it to degrees of measure. The trouble is now the graph has been squished because all of a sudden Desmos extended the x-axis for hundreds of degrees. So we've got to stretch our y-axis, and that is ridiculously easy. Go in here, type in 50. It certainly seems to have worked. So we zoom out, and there's our sine wave. Exactly as we were expecting it in math class. $90, 180 degrees, 270 degrees, 360 degrees, and 0. Those are the parts of the wave you expected to see. All right, so here's our plot on Desmos. Who needs graphing calculators anymore? I want to make a new wave to be a companion for this one. So I'm going to go here and create an identical companion wave. It's sitting on top of the other wave. I want to nudge it over a little bit. You are used to this formula by now. What changes have we made to it? We have changed this to 50, and the x has become sine of t. What I want to know is what would happen if, instead of altering the b, we did this. We altered that x value slightly. So I went in here and I tampered with the x value like we've been doing for a little bit. And I sneakily add something to it, like 10. So every time someone goes to put in 0, they've accidentally got 10 going in. Anytime someone wants to put the number 1 in the formula, it changes to 11 on them. So let's do that. Let's go in here and change that. Now we have to make sure the sine function continues to operate on the t. So we put it in brackets, and I'm going to go plus 90 and close those brackets. What has this done? This has simply gone ahead and shoved the numbers over. And then it erases it on me. So we'll do this again. 50 sine t plus 90. What it's done now is when t was 0, it's gone ahead and shoved it to the number 90. So it's actually shoved the curve to the left. 0 now becomes 90. 90 becomes 180. The other function wasn't tampered with. So it slid the function sideways. And I can change that value by simply altering the number of degrees it's pushed the graph to the left and the right. Now, it's awkward looking at these two when they're landing on top of each other. So if we go back to this, and I'm going to take away all this stuff and put it back to the way you're used to seeing it. What will happen if we take a function and we put a b value in? What's the only thing it does to the line? It shoves it up or down. If you take a plot like this, you plot a straight line like this, and you put a b value in, all that's going to happen is the line will go up or down the graph. And if I put it on the edge of the graph here like this, you've worked with that. So this line now, the b value that you were taught about before, that intercept value, is this little height from here to here. The same thing is going to happen if we do it on Desmos. So I'm going to take the first line and I want to send it up the graph by 100 units. So I'm going to put in 100 plus. And what it's done is raise it up the graph by 100 units. And this one I'm going to send downwards by 100. Minus 100 plus. And what this has done is given me room in between the two graphs to plot their addition. Now, I still think they're kind of close together, so I'm going to take it then and change this to 150. Learn to just play with these things until you're as comfortable with it as your cell phone. You didn't learn all the features on your cell phone by reading the manual. You did it by playing with the phone. Play with Desmos. Now I've got some space and I want to plot the addition of these two waves. And I want to plot it right on the center line. So I'm just going to write y equals sine t plus sine t plus 270. Now, where is it? We forgot the multiplier. We forgot the 50. Okay, so that's caused it to disappear. Now, how do you want to put the 50 in there? Do you want to put a 50 in front of each or put a 50 up front? It doesn't matter. I'll put a 50 here and a 50 here. Okay, what you're looking at now is the addition of those two waves. This is what happened when we added up the wave on the bottom with the wave on the top. If they met on the water and they were traveling along together, this is the result of those two waves interfering with each other. What would happen if there was no gap between the waves? In other words, this offset, I change it to 0. Now the black wave and the red wave are perfectly lined up. What would the addition of those two look like? It would look like that. Okay? Now, what if I shove the two waves 180 degrees apart. 180. Now the black wave is completely opposite of the red wave. They are now what's called out of phase by 180 degrees. The crest of this wave will meet the trough of that one. The crest of this one will meet the trough of that one. What do you think their addition will look like? Let's find out. We'll change this to 180. Where did it go? This wave completely destroyed itself. When Superman and Bizarro Superman meet, they canceled. This is the matter wave. This is the antimatter wave. This is equal and opposite. The waves completely killed each other because they were completely out of phase. What if they were almost out of phase? What if we put 170 in there? Then you would hardly notice that these two waves don't line up and something survives. Now, is there an easier way we could automate this process? Yes. Waves are called in phase when they line up. So in phase means the peak on one wave and the trough, the other wave is lined up with it. That would be in phase. Okay? When they start to drift from each other, we call that out of phase. So I'm going to go back to this. I'm going to capture him, pull him down. I'm going to turn him blue. I'll make him blue. Your dog doesn't love you anymore. Now he's blue. Okay, let's see. I'm going to take this wave. This wave is in phase with the other one. Now it's 90 degrees out of phase. Now it's 180. Okay, 270, and then eventually back in phase again. Why do I say it's back in phase again? Well, because it's a wave. There's lots of them. Okay, there's more and more of them all the way along. So this is just one. So what could we do to automate this phase process? Could we put a letter in here and Desmos will allow us to play with it? Yes. What should we call phase? Well, you might want the letter P. And you can use P. But P is not F. There is a Greek letter F that doesn't exist in English. And it's called Phi. Did you see that? Watch again. I'm going to go in here and I'm going to spell F. P-H-I. And that's the letter that we don't have in English, which is good because I spit all over my screen. Do you like phi? Can you live with it? Then use it because you will be by first year university. If you can't live with that new letter, don't bother. Why do we pick I? Because it sounds like phase of the wave, and that's why we choose phi. Once upon a time you didn't like theta. Now you accept theta. So don't be phi-phobic. Okay? Now, can we make this turn to a slider? Yes. We can make a slider out of it. Okay? And we can set this slider. Now this is degrees, right? So we want to change the range of the slider. Did you see what I did? I clicked the range. We want it to go from 0 to 360 degrees. And what step shall we take? Let's do 5 degree steps. And once you've done that, now these two numbers will change in time. Watch, it's so cool. I'll zoom in here. And we've got right now, the waves are totally in phase. The phase shift is 0. As I increase the slider, you notice the black wave is moving to the left. Now that I'm at 50 degrees, the crossing here is moved 50 degrees over. And now the addition of the waves is looking very different. So as I move this slider over, we're going to get to the point where the waves kill each other. Lo and behold, 180. Okay? So from a distance, you can see that this is very, very symmetrical. So this is your first experiment with adding waves together where you can phase shift them. The one wave is being moved back and forth, and the middle wave is what is left over when the two waves collide. So this wave at 0 is undergoing total constructive interference. When the wave shifts by 180 degrees, the two waves go to total destructive interference. And this is not just applicable to sound, but it's an integral part of grade 12 academic physics. So next, we're going to go and see what this sounds like. When you open Audacity, you can generate a sine wave by simply going to Generate and then Tone. It will typically give you 440 hertz to start with. I switched it to 200 just because it's not as obnoxious of a tone. And then you've got minutes and seconds here, okay? So I'm going to put, I don't know, I'm going to have it generate a really long tone. Okay, there it is. All right, now let's duplicate that. But first, let's zoom in. I'm holding the control key and using my mouse wheel. I've zoomed in so we can see the wave. We're going to duplicate it. How do you do that? Edit, duplicate. There's the duplicated wave. When the two play together, they're going to be twice as loud as before. But if what we just learned is we can create the cancellation of these waves. Now, there's all these tools up here on Audacity. The one that's really important is this one. This one is the time shift tool. If you click the time shift tool, you can drag the wave over. So I'm going to just hold and I'm going to move this wave over a little bit. And then I'm going to hit play. Notice it got quieter. Well, let's try something here. I'm going to go Control A. That means select all. See here? Control A. Now that I've selected them all, I'm going to go to Tracks. Okay. Mix. And mix and render to new track. This is the result of adding those waves up. Now the problem with Desmos is it's doing volume addition, something that wasn't being done in Desmos. So you see this, but that's the result of the wave being added. Okay? But I want to try something here. Get rid of that track, and we're going to time shift this one even more. Slide this one over. See, it's grabbed both. That's because I still have everything selected. So I click off anywhere, and now I can just move this one. And I'm going to see if I can completely kill those waves like we did in Desmos. Look at that. I almost perfectly destroyed them. Now, is there any way to get in closer and try? Yeah, there are ways of doing it, but you can play and you can... Look at that, almost completely gone. So you can actually use these programs to simulate the same thing you just saw in Desmos, but now you can hear the result. So again, if I press Control A, well, first thing I'm going to do is I'm going to turn the volume down a bit. I'm going to bring this volume down to -10 and this volume down to -10. That way when they add up, they don't go off the window like you saw. Press Control A, Tracks, mix, mix and render to new track, and there's the addition of those tracks. You see, they almost completely canceled out. And the cool thing about Desmos is when you zoom in really close like this, you're seeing the actual XY data sampled through your computer. So we can get that. Now, can Desmos do this on its own? Oh, yes, it can. Watch. Get rid of these two waves. Take the original wave. We'll go backwards to the beginning. And we're going to go Edit, Duplicate. Didn't select a wave. Control A, Edit, Duplicate. Now select just the second track. See? Now go Effects, Invert. Gone completely. You succeeded in creating total destructive interference by using that invert tool in here. So not only are you seeing what you can do with these waves, but now you're getting the basic idea how we do noise reduction in the real world. So if we want to improve the sound quality of something, we can find a wave we don't want, and then we do a 180-degree reversal of that wave. We completely shift it out of phase, and then the noise gets completely canceled.